Now then, we have an exciting display in store for us with our special guest, Dr. John Kilcoyne. So, Dr. John, what are you going to show us first?
Well, first of all, Emma, I have got some magnesium metal. And as you can see, magnesium metal comes in the form of ribbon. I have absolutely no idea why, because you wouldn't want to walk around with this in your hair, would you? Because you look so stupid, and also it hurts. And thirdly, you'd be vulnerable if somebody approached you with a match. So I'll just show you the oxidation of magnesium, which is very easily done, and there is an evolution of energy in the form of a very bright light and some heat. And it's better not to look at the light for too long, or you'll get a green spot in front of your eyes. But there we go, and you can see this smoke rising is simply magnesium oxide, and this tail here is magnesium oxide as well. If you just blow, you see, you've blown it off. Now, whilst you may have thought that was maybe slightly more interesting than watching paint dry, I bet you're not thinking it was the most interesting thing you've ever seen in your life.
No, not particularly.
But if I take this magnesium metal and we grind it into a fine powder, and we mix it with a chemical called an oxidizing agent, which can give it some oxygen, and we put it in a little pot like this, then we can make it more exciting. So if you just like to take a step back with me, and if we can, make sure we get the right one. Are you ready?
Yes.
Now there. Did you think that was more or less exciting than the ribbon?
Definitely more exciting.
Definitely more exciting, more smoke, and in fact, I think we better have another look at it, do you? Because it was enough. It was exciting enough to want to have another go, wasn't it? So if and of course, observant people will have seen that there's a similar pot here, and this is the same amount of material. The only thing with this is it's got a lid on, and it's only paper, so we needn't be too worried about it. And this is what happens when you do it with a lid on. Are you ready?
Just about.
Are you sure? There you go. Now you'll have noticed that was slightly different to this one.
Just slightly,
The lid making a difference. In fact, what it has done, it's turned that, what we call an exothermic chemical reaction, one which gives out heat, into an explosion. And that is because when confined spaces, pressure builds up, causes reactions to go faster, and they go faster and faster until the pressure is so great that it bursts out. Now, I'll show you some more oxidations. They won't go bang again then, so you needn't get too worried about it. Here's a dark coloured powder, and it's an oxidizing agent. It wants to give its oxygen away. And in this bottle is a colourless liquid which is absolutely desperate to get some oxygen. Okay? Wants to give oxygen away. Wants some oxygen. Chemist. Good fun, eh?
Yes.
Yeah? So we put this on. Now the problem with this, Emma, is that there is often a delay. And so there it goes, not much delay today because of the heat of the lights. That's what we call a spontaneous combustion.
Right.
You can imagine in winter, if that's much slower, it sometimes goes off in my car when I'm on the way home.
Right.
And there's a conversation that usually begins, "Your boot's on fire, sir." And, well, you can imagine, I always say, "Very sorry, officer."
Yeah.
Anyway, now, we'll just do one more of these oxidations, shall we? Just for fun.
Just for fun.
And this is a white, it's good fun, isn't it? Yeah. And there's a white powder there, and it's a mixture of two chemicals. One chemical wants to give the other one oxygen. But in chemical reactions, more often than not, there's an energy barrier. They can't just get a start, you know, and they need a little kick. And concentrated sulfuric acid, that usually does the trick. So are you ready for this one? Hey?
Wow. Now that's pretty.
What do you think to that?
That's really nice, that's really pretty.
You see that lilac colour?
Yeah,
That is the flame colour of a potassium atom. That's that you see in there. And it's rarely seen because most potassium salts are contaminated with sodium and it swamps it with that yellow colour of the street lights or when your pan boils over. What we can do now is we can look at the calorific value, the amount of energy that there is in a single midget gem.
Wow.
What do you think to that?
So what made you get into science then?
Well, when I was 10 years old, or 11, somebody bought me a chemistry set. And it was in the days when chemistry sets were chemistry sets.
Yeah.
And they were very exciting and I really liked it. And when I went to secondary school, I did science and chemistry and I liked doing it and I was good at it. Are you ready?
I think so. Oh.
What do you think to that, Emma?
Wow, that's lovely, that.
See that, Lilac?
Yeah.
Hey? Now, some people do that with a jelly baby.
Oh, right.
And it's known as a screaming jelly baby.
So what have you got for us now?
Well, the last time we were looking at hot things, burning things, things that were giving out heat and energy. What I've got for you now is something that's really cool. And what it is some liquid nitrogen.
Right.
Now, liquid nitrogen is just nitrogen from the air that has been liquefied, and it's in here, and it boils at minus 196 degrees Celsius.
So it's very, very cold.
Very, very cold. If it were just 4 degrees colder, it would be twice as far from the zero on the Celsius scale as boiling water is, but in the opposite direction.
Yeah.
So it's very, very cold indeed. And it's in here, it's boiling away. And just to show you that things contract on cooling, I've put this balloon in. Very, very cold this. And as this warms up, it will expand, the gas inside will expand, as you can see, and I'm now wishing that I hadn't been to Pound Stretcher for my balloons.
Why?
Because they often don't survive this little exercise, but I got 200 balloons for £1, you see. Hey? But anyway, this one's surviving all right so far, isn't it?
There we go.
What do you think?
Wow.
Hey? Do you want to say that again?
Yeah. Let's
Thought you would. Eh? I thought you would, and even if you said no, I was going to do this, because I like doing it. Oh, look. Hey, here we go. Now, I'm going to show you some liquid nitrogen now. So if it splashes on you, it won't hurt you.
Right, well, I'll
Okay,
stand
so
back.
just stand away. I'm going to tip it over the bench, and it'll roll over to the front there. Some will come backwards, but that's okay. Are you ready?
Yeah. Look at
Good,
that.
isn't it? See it? Rolling about
Now
on
that
little
is very
cushions
cool.
of
Yeah.
nitrogen gas that form at the surface there. And the thing is, if it falls on you, it evaporates away so quickly it doesn't have time to do a nasty burn. So this is what we mean by a cold shower. You stand back if you don't want one.
I don't want fancy one.
Here we
no.
go. Now this, Emma, is what you call a cool dude. Hey? Oh.
Very cool.
Do you know how refreshing it is in these lights?
I know, I'm sure it is.
Hey? There you go, look.
I don't fancy one myself though.
Do you not?
No.
Look, it's nice. Hey? Now you see what it's done to this rubber tubing?
Yeah.
Because I'll just show you, look. I'm going to take that rubber tubing out. And here's a fresh piece here. And This is a rubber tube that's bounces, it's elastic, and this is a frozen rubber tube.
Wow.
There you go. And that's because it's all brittle and solid. We'll just get rid of those to the side there. Now, the other thing about liquid nitrogen is, or the other thing about liquids generally, when they convert to a gas, there is a very, very large increase in volume. So if you actually take only 35 millilitres of liquid nitrogen,
right,
and it converts to a gas at 25 degrees Celsius and 1 bar pressure, it occupies 24,000 millilitres. So it expands from 35 to 24,000, and we can kind of illustrate that with this little experiment. And if we put liquid nitrogen in these Buchner flasks, like this, and if we put these bungs in, and if you and me, I hate it. Oh, now you bet your bets, Emma, on the yellow or the oranges. Oh, and the yellow takes it. The orange, oh no! There we go.
Now that was exciting.
That was exciting, wasn't it? Anyway, you'll recognise this.
Banana.
Yes. And you're not in the Society for Prevention of Cruelty to Bananas?
No, I'm not.
Okay, well, in it goes then. And as you can see, the nitrogen is boiling uncontrollably.
It is.
That is because this banana is more than 200 degrees Celsius above the boiling point. So it's like putting a red hot piece of metal into a bucket of cold water. Of course, at the same time, the banana is cooling, along with my fingers and thumb, which we try to preserve. You have to tell young children that science is a wonderful and a beautiful and a noble thing to do, because we've all been so lucky to be born into such a fantastic and magnificent universe.
Oh yeah, definitely.
And we can't help but try and fathom its laws and ask questions like why the sky is blue and not another colour, and why is grass green. And it's not. There are no ethical questions. Well, I mean, there are ethical questions in that you can't do experiments that hurt people. But once we've made a scientific discovery, you see, we human beings tend to use it to do things that we want to do. And there you've got a moral aspect, because mostly you can use it to do really good things and help people, make their lives easier, or you can do wicked things and make their lives miserable. But the pursuit of the knowledge itself can't be wrong. It's what we as human beings want to do with it, and everybody has to make those choices and those decisions. And there'll be more and more of them as the world becomes more and more technologically based. Which is why young people should study science, if you were thinking of asking me that question. Anyway, can you see it slowing down now?
Yeah,
That's because the banana is reaching temperature. And I want you to imagine now that you have been very, very unlucky.
Okay.
And that your fence has blown down in the gales.
Okay.
Now there's your fence. Okay? That piece of wood will have to do as your fence.
Okay.
And to mend your fence, you need to knock that nail in. And guess what? You've lost your hammer.
Boo.
So, rich people, off to B&Q, buy a new hammer. Okay? Boring people, look for hammer. Exciting technological people, go to greengrocers and buy bananas. Go to liquid nitrogen shop, buy liquid nitrogen, freeze the banana in the manner shown, and then use the banana to hammer in the nail. Ha ha. It's all right laughing, hey? It's broke, my banana snapped. Anyway,
Good.
I could now pretend for a joke that I'd nailed that to the table, couldn't I? To upset the university. But I won't, because I haven't. Anyway, all technology carries with it risk. The risk with that is you get hold of the wrong end. Guess what then? It fuses itself to your hand and you're off to accident and emergency to have your banana removed. And a very embarrassing interview with a junior doctor, but we won't go into that. Okay, and that is the liquid nitrogen story.
Wow, that was very exciting.
Yeah.
So what are you going to show us now?
Okay, this is known in the trade, Emma, as either a blue devil or a barking dog.
Okay.
And there are lots of them on YouTube under those names. But effectively, it's the reaction between nitric oxide gas, which is already in there, and carbon disulfide. So I have to get the carbon disulfide in, and carbon disulfide is a volatile liquid whose vapour has a characteristic odour.
Okay.
That means this stinks.
Smells.
And it stinks like rotten cabbage on a terrible Monday morning. Let me know when you can smell it. Oh, please help me. Oh, now it's on my fingers. Look. Dear. Now, when I take this lid off to put this in, you'll see some brown fumes at the top.
Okay.
That's nitrogen dioxide. It's the nitric oxide reacting with oxygen in the air to produce nitrogen dioxide. Did you see them?
Yeah.
Good. But you know what the snag is? The snag is that I can't leave them in there when I set light to it because the ferocity is too great.
Right.
However, nitrogen dioxide dissolves in water to give nitric acid, and this is what we're doing now, and hopefully it will be just nitric oxide and carbon disulfide that remain in the tube, in the gaseous phase, and we might see the little bubbles of carbon disulfide floating on the water there. Right, now, somewhere here, there's a wax taper, look. Fairly poor one because I couldn't find a church that wasn't locked. And there's my lighter. Now just stand back a little bit.
Okay.
Are you ready now?
I think so.
That's good. Here we go. Are we all ready? Here we go.
Wow.
There you go. Now that's the barking dog or the blue devil. All of that yellow deposit is sulfur from the carbon disulfide. In the early days of photography was invented in 1837. In the 1850s, we've seen a Victorian lady who's had a portrait taken with her hat and her bustle and her long dress and a little handbag. Looks like she's had the biggest shock a human being could have. That's because that's how they did the flash.
Oh, yeah.
But they didn't used to tell her. They used to say, look at the camera, pet, smile. Ah! And that was that. So there we go, the barking dog.